Hi again, guys, and welcome back to Advanced Programming in C#. This time we'll look at abstract data types, and we'll start out by looking at linked lists. A linked list is an abstract data type, as said, and it's used to store data in it. So what is an abstract data type? Yeah, we have been working a lot with abstract data types, and an abstract data type is simply just a class that stores data for us. So, an abstract data type actually consists of two areas. The first area is, as we see on the left here, the list, which contains lots of methods. It contains an exist, equals, find all, add, stuff like that. But it also contains an area that might contain a class. It might contain several classes that are not public available, which means you cannot see what happens there. In this piece we'll actually look at what happens behind the scene, and you'll be coding some of it. So we have the front end, which is what can we do with this abstract data type, and the back end, which is handling all our data. So if we have a linked list, we would almost certainly have a class that calls that is named list or linked list or something like that, which contains some functionality. So in this case we have a linked list that is empty, which means we have a reference in it that points at null. We haven't added anything yet, so let's add something. So now we have added a fish. So our linked list points at the fish object, which is some data that we have added, and fish is pointing at null because there's only one object in it. If we add the cat after the fish, it could look like this: cat first, fish then, null. So null is telling us that there are no more elements in the list. We can even add a dog. That means that our behind the scene class may look like this. Data, in this case it's a string, and it is pointing at the next element, which is of the type linked list data, which is the same as the class we have already. We could argue that we might save other stuff than strings. What if we wanted to save an integer instead? CPR number, an advanced type like an object with address and human information of all kinds of stuff, eye colors and height. So this class could in fact be a T representation instead, because then we don't care what kind of data are stored, but we still have the next. So how does we actually add the dog to a list that is already there? We can see all the arrows are pointing to something else, which is the next object, and fish, which were the first, fish.next will point at null. Now we have created a dog. So dog is by itself, and dog is pointing at null because it's not in the list. So the first thing we take is whatever the lists point at, we'll let the dog point at as well. And then we'll say the list should not point at the cat anymore, it should point at the dog. So now we're there. It's quite simple. So now we have a linked list. And we use it like this. You can see that I have called my public class list for linked list. And I have at least the functionality of adding stuff, as we have seen, so I can add fish, cat and dog. I have created here an add function for you, so you can have something to start with. And you can see down here that I have the linked list dot next, the linked list data dot next. I set that equal to the first element. And you can see that my linked list contains a first element reference, which at the moment is pointing at dog. What will happen if I want to remove the cat object from the list? Quite easily. I'll just let the dog point at the fish. just like that. And then I remove the cat pointer, and then the garbage collection would take care of the cat object by itself at some point. The garbage collector is a mechanism that will destroy any object that has no referencing pointing at it, and as nothing is pointing at cat at the moment, it will be deleted later on, like this. I could also create an exist method on the list. It will return true in case of cat, and it will return false in case of it went all the way through. So the algorithm is here. If you started looking at the list, it says, is the first element cat? No. Is the next element cat? Yes. Return true. If we were asking for a giraffe, it would say, would the first element be a giraffe? No. Would the second element? No. Would the third element? No. Would the fourth element? Oh, wait a minute. There's not a fourth element. Okay, then I'll return false. It wasn't there. The algorithm would look something like this. So I'll start off saying linked list data has an object reference to that pointing at the first element, which is dog. Then I said, as long as my linked list test object is not null, then I'll continue. It is not null as long as there's something in the list. And I said, if it's equal to the data I'm looking for, return true, otherwise go to the next. So setting the pointer to point at the next object, and then do it all over again. Try it out. It's not that difficult, and it's actually a bit of fun. But we're not finished yet. You can add lots of functionality to the list. For example, how about converting our object list into a real list? Or how about removing the cat object from your data? Or even better, how about changing it all to do it in T objects? If I were you, I would still prefer strings at the beginning because it is easier to get started with, and then you can change string to T objects, as I showed you in one of the earlier slides. Maybe instead of bool, you should return the T object in the exist. If a cat exists, then just return the cat. You know, if the cat doesn't, if the object you're searching for does not exist, it will just return null. So you can actually use it to get an object out of the list. And instead of adding to the first element, which seems a bit illogical, why not add it to the second, to the last? So it will be ordered in the other way around. So the exercise for you would to be creating a linked list with the add, exist and remove functionality. You can do it either with a string or with a T, I don't care, but start with the string. There are lots of other abstract data types. Here I have shown you a stack, a queue and tree. There's a meaning with why it's upside down, but we'll look into that in a few seconds. So the queue, we all know a queue. So a formalized computer queue is you have two methods. You add stuff to one end and you by in-queuing it, and you dequeue stuff from the back. It's that simple. You have two methods. They may contain account, exist, toList and stuff like that, but the primary functions here are in-queue in one end, dequeue in the back end. And when you're dequeuing stuff, they are actually going off the queue, like a remove in the linked list. Again, it's the same thing. We have a class that is public with lots of public methods like the in-queue and dequeue and count and exist. And then we have the data. So a list could look like this. We have an entry door where you add people, and then we have the bar that fulfills people's wishes and grant them a drink. take them out of the queue. I usually use queue when I'm logging data. So if we look at here, we have a file writer and we have an entire program, and in this entire program I log stuff, so I can figure out if the customer did something good or bad. Why did my program fail? I can look in the log to see what the customer did before it failed. The problem with this is it takes a few milliseconds to write a log, and this means that for me to do some debugging stuff that might come in handy later, I'll make the entire program run slower. The customer might not like that. So what I instead is doing is, whenever I want to write to the log file, I write to a queue instead. And then I have a separate thread that is dequeuing stuff and writing to the log file. Now it will only take me a few microseconds to add stuff to the log, and the slow writing to the log file will be done later or in parallel. I have a simple tree also here, and in our simple tree we can insert stuff and we can check if stuff exists. And our data object here, the behind the scene data object here, contains the number and a reference to all the numbers that are smaller and all the numbers that are greater. So we have three properties in each object. Again, it's the same thing: stuff that are public, stuff that are not public. So my insert and exist is in the public part, and my int number data objects, bigger and smaller, are in the data part. So how would we know that the number 32 exists in our collection? Easy enough. If we look at the root, which is what our public area is pointing at, says, oh, 50. We are looking for 32, and 32 is smaller than 50. So we'll go to the left. Oh, 21. 21 is lower than 32, so now we'll look at the right. Whoops. Oh, null. That must mean that 32 is not in our collection. Easy. We also have a different kind of abstract data type that is called a hash table. I'm trying to illustrate it here. If we have an add and a get, and hash tables are very interesting. So we have here an 5-element array, which is in the data part. We have these hash function, which is in, it's a private method, but in the public part. We'll look into that later. And in this case we have already stored monkey, cat and chimp. So what will happen if we want to add a bug? We'll add bug to our hash method, and it will put out by magic the number 1. I like that. This means that bug goes to number 1 location of our fixed size array. Cool. If we want to add a dog, for example, dog, oh, that gives us by magic the number 2, which is the index of where dog should be. This means that whenever I want to check, do we have a bug, yes or no, I'll just put in my bug to my hash function. It will turn out 1, and if 1 says null, then we don't have a bug. If it has an object in it, then we have a bug. Cool. What happens if I want to add a muse? Yeah, muse adds by magic, it will return null as 0, but there's already a monkey in type 0. What do we do then? Yeah, we have learned about linked lists, and this is one of the proposals, is to say, okay, then we turn monkey into a linked list, so we can have each fixed size array element is not even an array element, it's a linked list. So we can add a mouse, for example. In this case, it's pretty easy to see that our hash function is just turning the first letter into a magic number. There are all kinds of hashing functions. And as you can see here, the hash function is what's doing the trick, and the fixed size array is in the data area. And it's important it's a fixed size array, because you don't want to resize it, because then you have to change your hash function. The hash function has to put out index numbers that matches the fixed size array. So if you have a fixed size array of 10,000, the hash function must take in the input and put out an output between 0 and 9,999 to match the fixed size array. The magic is, though, that big O of n on a hash table is 1, which means regardless of the amount of data, it will always take the same time to add and retrieve data. That's not entirely true if you're using linked list, so this is only when the hash table is in play. And the real difficulty here is to create a good and fast and reliable hash function that has the same predictable outcome with the same input. That is the algorithm, and it's not that easy. It also has to create a widespread use of the array to minimize the use of linked lists. So in the ideal world, regardless of what I put as input, I will always get an index number that is not in use unless it is exactly the same element. Can you see the problems here? Then we have a stack. Stacks are useful in, for example, pocket calculators. Stacks have two methods: a pop that will add to a push and pop, where push adds stuff to the top of the stack and pop takes off the top element of the stack. Again, the same thing. On the left we have a class that has all the public methods, and on the right we have the data area. So we can push stuff and we can pop stuff, but always from the top. So now to the exercise. Well, you should do the linked list as its basis of all the other stuff. But then I'll want you to do either a queue, a simplified tree, and there are lots of different kinds of trees, so this is just the most simple tree. A stack and/or a hash table. And just the last minute comment here is to say you should do them to get to know the techniques and the pitfalls and all the stuff. But Microsoft has provided us with lots of abstract data types, and we all know the list, but we also have the queue and the dictionary. And the dictionary is kind of the hash thing. And here I just have some examples with strings and integers. And they have done an even better job, because they have also these concurrent collections, which means that they have built in the locking mechanism so you can use them in a multi-threaded, multi-user environment. For example, the concurrent bag, which is a big blob with stuff in it. And then there's the concurrent queue, which I use a lot when I do logging, as I mentioned earlier. And the concurrent dictionary, which is kind of a hash table, but not quite. The functionality is like a hash table, but I'm not actually sure how they implemented the behind the scenes stuff, but it's implemented in both a fast and a very dynamic way. So again, thanks for listening. Bye.